Okay, welcome everyone. This is the F-star seminar, and we are grateful today to have Nik, who will be talking to us about how Z3 works under the hood in F-star. And do you want questions in the middle or at the end? Probably in the middle.
Yeah, I think, thanks, Josh. It's like, I want this to be as interactive and informal as possible. So I'm just going to do a bunch of demos and walk through this new chapter that I posted last week. So do ask questions as we go along.
Okay, and I'll be monitoring the chat as well.
Okay, great. Thank you. So I thought I'd start with just a really, just a few introductory remarks, I suppose. I mean, you all know that F-star uses Z3 to automate some proofs, and you've probably seen that as you go to larger developments, controlling Z3 and making proofs reliable can be a challenge, and or like Alex was saying, trying to get proofs to go through in milliseconds may require a lot of tuning. So this chapter is about how F-star encodes verification problems to Z3 and provides a few sort of tips and tricks for how to understand that encoding and how to profile Z3's performance on instances of queries that F-star presents to it. I'm going to start this presentation with just a few sort of hello world SMT examples, just so that we're all on the same page about what we're translating into. So here is a SMT2 file. SMT2 has a S expression like syntax based on languages like Lisp. And when F-star calls SMT, it sets a few options at the beginning. So I've kept those options here. MBQI, I think the details of these options don't matter too much, but MBQI is model-based quantifier instantiation, which we disable. So the way an SMT2 theory is structured is there's you declare some symbols that you're going to use. In this case, we have a function symbol f that takes two integers as arguments and returns a Boolean. And when you declare a function symbol in SMT, these are uninterpreted functions, meaning that the only thing the SMT solver knows about f is that it's a function. That is, it takes equal arguments to equal results. The notion of equality is built into the SMT solver. It has knowledge of equality, and there's equality available on every sort. So int and bool and so on are called sorts in Z3, and every sort has a notion of equality. Then what you do is you can assert some facts about the symbols that you've introduced so far. So assert, just so that we're on the same page, in F-star, an assert is when you write an assert, you're asking F-star to check that the formula that you're asserting is valid. In SMT2, an assert is like an assume. It just says, assume that this fact is true about f, and proceed with the rest of the theory. So here, what I'm assuming is that I've effectively just given a definition for f. I'm saying for all, and here's SMT2 has support for quantifiers. So this is saying for all x and y, which are both integers, and then this is the body of the quantifier. The body of the quantified formula, SMT2 has an attribute mechanism where you can decorate a term with an attribute, and that thing has to do that. You start a term with this bang. So don't be confused about this bang and logical not. We had some conversations about that on the Slack. So this is just an attribute, and the attribute is saying the identifier of this quantifier is this symbol, definition of f. And the definition of f is just that if y is greater than or equal to x, then f of xy is true, if and only if, in both directions. Okay. So I've assumed this fact about f, and now I want to check if I want to check that some fact is valid. The way this usually works, and the way F-star uses it too, is you assert the negation of the fact, into this context with the other assertions in it. And then you ask the SMT solver to check if the collection of hypotheses that you have about F and the negation of the goal that you want, if that is satisfiable or not. And if the SMT solver, and that's what this is, that's this check sat. And if the SMT solver says unsat, meaning that there is no model in which there is an assignment for F, an interpretation of F, in which all these facts can be true, then you know that that your negated query is valid, or the hypotheses that you had up to this point are already invalid. Meaning, in the context of a program proof, that would mean that you're on some unreachable path of your program. You all with me so far? Any questions? So we can feed this to Z3. So here you can start Z3 simple.smt2, and it very quickly says unsat. Okay. So now one of the things I kind of wanted to a big focus of this chapter and what I wanted to convey to all of you today was how quantifiers work in the SMT solver, and in particular how quantifiers are instantiated. So here, when you have this assert for all in your context, this is like a hypothesis. So think of this as we're really asking the query. The query is something like this. It's saying, we have the definition of F in our context, and we're asking if this formula is derivable. We're asking if it's true that for all x, y, z, f of x, y, and f of y, z implies f of x, z. Right? That's kind of the query we're asking. All right. So this definition of f is a quantified formula in the context. And when you have a universally quantified formula as a hypothesis, the SMT solver this formula is completely inert. It's not going to interpret it at all until it can find an instantiation for x and y. Meaning it has to find values for x and y so that it can instantiate this quantifier, and then it gets this fact, this non-quantified fact, and then it can reason about it. So a lot of what's going on under the covers is how the SMT solver figures out instantiations for these bound variables. And to just illustrate how that works, we can add something called a pattern to this. And a pattern is you can write this. And what that says is that a pattern is a term or a collection of terms which collectively mention all the bound variables. And what the SMT solver does is that when it's searching for a proof or when it's trying to prove that your theory is satisfiable or unsatisfiable, it's building a partial model of your theory during the search. And in the process of this search, any term that already appears in the partial model is called an active term. So think of this as like these terms may be like goal formulae that it has to prove so far, or it may be formulae that it has as hypotheses. We don't necessarily know what the truth assignment of these terms is, but these are terms that are currently being explored by the SMT solver. So if it finds that there is an active term whose head symbol is F, let's say in its search, it's going to find an active term of the form F of, say, F of 0 and 1 as an active term, then it notices that there's a quantifier whose pattern is F of xy. And what it's then going to do is it's going to instantiate X. It's going to sort of match the active term against the pattern, finding a substitution for the bound variables. So in this case, it's going to find X is equal to 0, Y is equal to 1, and it's going to substitute X for 0, Y for 1, and then get this non-quantified fact, which would be, if and only if 1 greater than 0, then f of xy, f of 0, 1. right? It would get this ground fact into its context, and then it can use this fact to reason about stuff. Okay, so until it finds an instantiation for the quantifier just does nothing. Okay, so to give you an illustration of the fact so here I put this pattern in there, and Z3 will still say unsat, because by default, if you don't write a pattern, Z3 picks a pattern, and the rule that it has is that it picks the smallest terms, the smallest subterms of the body that involve uninterpreted function symbols. So it will not pick pick this term, because greater than or equal to is an interpreted symbol. It's a symbol in the theory of arithmetic. But it's going to pick this term as the pattern because it's a small term in the body that mentions both bound variables. So by default, this is what it picks. Okay. Now I can do something artificial and say, suppose I say declare font G and let's say, and I make this my pattern, right? What do we expect will happen here? Anyone? Well, right? So Z3 says unknown.
Syntax error, you return int, and the if says bool.
Good question. So notice that I've only used G in the pattern, and a term in the pattern does not have to be Boolean, or it can have any sort. So it does not have. So this is fine. Like syntactically.
Yeah, no. But if and only if has two arguments, first of which is bool and second of which is int if your function is int.
No, but this remained f, right? I only changed the pattern.
Oh, f. I somehow thought that you didn't substitute the function.
No, I intentionally left this as f and just changed the pattern to G. Okay, so what I wanted to illustrate is that if I have a quantifier and its pattern is a term which will never appear as an active term in the proof search, then this quantifier is never instantiated. There's no G around, there's no assertion involving G anywhere. So there's no way for Z3 to instantiate this quantifier with an active term that mentions G. And so this particular checksat invocation returns unknown because it can't prove whether that this is unsatisfiable, nor can it conclude that it is satisfiable because this is a quantified Z3 when working in with theories that involve quantifiers will usually never return sat because it can't decide. I mean, if it's using this heuristic of quantifier instantiation to decide if a theory is satisfiable or unsatisfiable. If it can't find the right quantifier instantiations, it's not going to say that the theory is satisfiable because it may not be. It's just going to say unknown. Okay, so this was my first demo showing you that, giving you some idea of what patterns do and how patterns are really important to ensure that to get the right instantiations of quantifiers. Okay, now, so let's go back to a state where this thing actually works. Now, is that a question?
So this first serve for early escapes. Like we do not know if things are satisfiable, but there are ways to escape early if they are not satisfiable.
I'm not sure I understood the question about escape early.
I mean, the mechanism you said most times it says either unknown or unsat, and saying sat is rare.
In a quantified theory, you will almost never get sat. That's just how Z3 works. Like it cannot prove that just because it was not able to find the right instantiations, it does not mean that the theory was satisfiable. So it will not reply sat. It will reply on.
So it only finds things that are unsound. I mean, the previous example was unsound. Like we first declared the partial order, and then we demanded it to be not transitive.
Mm-hmm.
That is unsound. Like
Yes.
any partial order is transitive.
Mm-hmm.
So Z3 only finds unsound statements.
No, that's not quite true. So all I'm trying to say is that if it finds unsat, then it actually can build a proof that this thing is unsat, and builds a proof of unsoundness of, as you're saying, unsoundness of the theory, right? If it said if it is unable to do that, it
Then
will
no
apply
info.
unknown, but it can also produce for you a partial model for the theory that shows a satisfying assignment, a satisfying partial assignment of the symbols in the theory.
And what we do with the partial
If you get
assignment?
that's the thing that
Okay.
F-star uses to report an error message. Okay.
We have a question in the chat, which I think is interesting. It's Philip asks if the partial model for unknown can be accessed.
Yeah, you can get the model. If I remember the right syntax for this. In this case, there's no model, but sometimes there would be. This is a very simple theory. There's this fact is not in scope. Maybe. Yeah, sometimes you get a model, sometimes you don't.
So the no model would be like assertion failed, right? Kind of error messages.
If you don't get a model back, then this is when F-star can't say much about which part of your query failed, and then F-star proceeds into splitting your queries into smaller pieces to tell you which part it failed, which part failed. But we'll look at that in a minute. I just wanted to do a second little demo at the level of SMT, and to give you a sense of, sorry. Here's another SMT theory. It's kind of similar to the first one, but here, instead of giving a definition to F, I'm going to assert that F is that it's an uninterpreted function symbol, but I'm going to assert that it is transitive. Okay, so this is saying for all xy, if f of xy and f of yz, then f of xz. And I'm then going to assert a bunch of ground facts about f. And then I'm going to ask if it can prove f of 0, 8. All right, and it's a negation of that. So I should expect this to be unsat. And in fact, it is. But I wanted to look at the choice of patterns here. So notice that what I chose as patterns here was to say that if there's any pair of active terms, f of xy and f of yz, that agree on this kind of middle value y, then you can use those two instances of f to instantiate the quantifier. So this is kind of a it's kind of a forward search style. It's saying whenever there are two facts of this form, the quantifier can be instantiated and a new fact can be derived. So let's think about what this means in this context, right? So this means that if I have f of 0, 1 and f of 1, 2, this quantifier can be instantiated and we would get f of 0, 2. Right, and then so on, and then now we would take f of 0, 2 and f of 2, 3 and derive f of 0, 3 and so on, right? And eventually we'd get f of 0, 8. Now, but what we would also get is we could instantiate with f of 1, 2 and f of 2, 3 and get f of 1, 3. Now f of 1, 3 is useless. The instantiation I really want is the one that begins in 0 and ends in 8. If I want to prove this query, that's the one I want. These additional ones like f of 1, 3, and I would also get things like f of 3, 7, sorry, the choice of these quantifiers essentially leads to a quadratic number of instantiations, because this pattern is chosen in a style of forward instantiation. For any pair of facts that agree on their middle value, you can instantiate the quantifier. So now if you look at, you can ask Z3 to tell, you can turn on a bit of profiling. smp.qi.profile equal true. And here on this particular theory, we see that this particular, sorry, let me just change the name of this. Transitivity of F was instantiated 28 times, right? And that's kind of what you'd expect from a quadratic number of instantiations of these many quantifiers, right? Of these many instances. Now, if you chose your quantifiers, your instantiation, your pattern a little bit better. So for instance, suppose we chose the pattern to be that. That's saying if my goal is to prove f of xz, then let that be one of my patterns. And if I can peel off the first, if I have a fact of f of xy, then my new goal becomes f of yz. Now I will no longer get instantiations of quantifiers of this form, because these are no longer, my goal is only f of 0, 8. So I will no longer get f of 1, 3, and so on. And this leads to a more efficient quantifier instantiation strategy. And here we can see, if we do that, now we get a linear number of quantifier instantiations. Sorry, I should have described this. This says Z3 instantiated the quantifier named transitivity of F 28 times. And these two things are, I mentioned them in the chapter a little bit. They're involved, they are related to a cost and some generation identifier and so on, some generation counter. It's less important, so I'm not going to say that much about it. But what's important here is that in the first case, this quantifier was instantiated 28 times, and the second case only 7 times. Okay, so when you're writing patterns for quantifiers, and we'll see how you can do that from F star, you have to think a little bit about what proof strategy you want the solver to use to find instantiations. And if you choose the wrong ones, you can end up with quadratic or even sort of infinite. We'll see some examples of like potentially infinitely instantiating quantifiers. So that's something to be aware of. Okay, so now I'm going to switch, unless there are questions, I'll switch to
yeah, there's 2 questions.
Yeah,
one is from me. So this rule is like a left rule in a sense.
mm-hmm.
So I assume you also want to add a right rule, or
Yeah.
maybe, so like in practice, would you do both, or would you only have one and then just remember to, be disciplined about this?
Yeah, you can write the other rule as well. You can write, you can write that one. And you can put them both, but it's usually better to just pick one and try to structure your proofs in that way. So
That makes sense.
Now, this example is not completely artificial. So for those of you working in Lodestar with the modifies clauses and so on, this is exactly the shape of how modifies clauses work. So in Lodestar, think of F as like you're saying, some set of locations, L, was modified between heap 0 and heap n. If you can prove that that set of locations was modified between H0 and H1, and that same set of locations was modified between H1 and Hn. So these kinds of transitivity style quantifiers, they appear a lot, and when you're using them, you should be mindful about how you write patterns for them. And to Josh's question, in the context of modifies clauses, the left one is actually quite reasonable, because you are moving through the states sort of linearly from the initial state onwards. So you usually have this fact around, and you don't necessarily have this fact around. You have the ground facts about small transitions, and you're trying to derive the big facts about large transitions. There was a second question you said, Josh.
Yeah, the second question is about an earlier thing you said. So when you do unknown, you can call get model sometimes, and fstar can tell you, for example, which query fails. Like, so I know that Daphne has some very limited support for actually finding counterexamples.
Yeah.
I'm wondering if that is part of fstar in any way, or if fstar just doesn't do that and only tells you which query fails.
FStar doesn't do that.
Okay.
Yeah. I think there's, I've heard from people who've used the counterexample viewer in, actually there was one in VCC before Daphne. My impression is that this was not really used that much in real situations. The models were usually not that informative, but if anyone has some has experience using this kind of thing in a profitable way, like I'd be curious to hear. Reach out to me afterwards. So I'm going to switch to fstar now, and here is it's a large fstar development called Zeta that Arvind, who is, I saw on the call briefly at some point, has been developing. And a few weeks ago, he reached out to me to say, hey, I have this proof, and it's taking forever to verify, and I'm getting like this really weird behavior. And what he said to me was, can you all see this? Is this big enough?
Yeah, can you make it a little bit bigger?
Can you please enlarge it a little bit?
Yeah.
Double it. Oh, perfect.
So he had this proof where strange things were happening, where he knows that xids underscore is equal to xids plus 1, and that it's less than this thing, but he's having to assert all these facts to prove very simple things that you'd think fstar would normally just know. Like, so strange stuff was happening here, right? So and in fact, if you try to get fstar to verify this, sometimes it goes through, sometimes it doesn't. Let's see what it does on this occasion. This assertion fails, even though it really ought to succeed. We know that it's less than that, and it's not equal to that, and this thing is equal to xids plus 1. So this assertion really ought to succeed, but it's failing. So so what I did to figure out what was happening here is once these kinds of things start to happen, I suspect there's something in the context that is causing the proof search to go into the weeds. So what you can do here is to do my kind of first recourse is to add a query stats. Try to see a little bit about what's happening, and can't see the bottom of my buffer. That's better. Okay. So this time, so fstar reported a bunch of these query stats, and it tried the query. So each of these query stats, it says it mentions the query identifier for this particular top level definition. The first query failed in. It repeatedly tried the query with increasing amounts of fuel. The chapter mentions a lot more about fuel. I'm not going to say too much about it in this presentation. And then it tried to split the queries in multiple times, and it some of them succeeded, some of them failed. So so query stats can tell you some information about which parts of your query are failing, where some parts are taking too long or not. But now, if you want to get some more insight into this, what I usually do is I'll turn on log queries, which gets fstar to dump an SMT2 file, and I'll also do a Z3 refresh, which means every query that's sent to that F star sends to Z3, it sends it to a fresh instance of Z3. So you get every query is kind of isolated without interactions with other queries that may be issued. And I usually also do a restart solver to start this thing in a fresh context. Okay, and once I do that, I can feed this to F star and Z3 again. And now I'm going to get a bunch of now it reports the files in which it's logging these queries. So the first one says, okay, here we go. Queries Zeta transaction serial x step.smt2. That's the query that failed. There's the SMT2 file. I usually set, if I'm in Emacs, I usually turn on Lisp mode because at least I get a little bit of syntax highlighting out of it and parenthesis matching and things like that. And it's a large file. It has 242,000 lines, encoding the entire all the modules in scope and a big query to Z3. So now I want to see what's happening with this particular file. So what I'm going to do is where am I here? So I'm going to do Z3 queries Zeta transaction x step.smt2, and I'm going to turn on smt.qi.profile, which is the thing we saw earlier, and I'm going to save the output into, let's say, zeta.qi. Oops. So this takes some time, and now I have zeta.qi, and it has these, what I'm interested in is these quantifier instances lines. So I'm going to grep for those lines. In zeta.qi, and then I'm going to sort by the number of quantifier instances. And I see here that
Do you mind making this bigger as well? Sorry.
Here, hold on. I think what might be easier is I just show you this here. And I haven't, that's bigger, right? It's not sorted, but maybe I should just do that. Hold on. So this guy says there's this quantifier, Zeta transaction serial spec serial 1, that has been instantiated 54,000 times. And so that's kind of my smoking gun. There's some quantifier that's been, it's gone a little crazy. So if I look in my query file and I search for serial.1, I find, here it is, equation Zeta transaction serial, I think that was the one. Yep. And I see that it's the equation corresponding to this definition in my program, Zeta transaction serial spec serial. So let's go look at what that is. Zeta transaction serial spec. And here it is. And here we see in F star a triple quantifier for all ijk. And without any patterns written on it. And if you look at this particular triple quantifier, there isn't a very good, any particularly good choice of what pattern you're going to pick for this one, because there isn't a term in the body of this quantifier that mentions all three bound variables. So this particular quantifier has been firing like crazy, and that's the source of our problem. So it turns out the way Arvind addressed this was to use a technique which we'll look at in a minute, which is to make this particular quantifier opaque and to control its instantiations manually rather than getting Z3 to instantiate it. So that's just to give you a sense of how you can use the quantifier, this very basic quantifier profiling in the context of a large program to find, hopefully, I mean, in this case, it worked out well. Like there was just it was very obvious that that this was the quantifier that was firing too much. Sometimes you may have several of these or interactions among several of them that are leading to problems, and that requires some more careful thinking. But this gives you at least a handle in, a starting point into how to investigate this kind of thing. Is that?
Do you mind going to the file where you had the multiple asserts?
Yeah.
So Alex had a question about exactly how do F-star asserts match Z3 queries? Like, is it one assert equals one Z3 query, or is it somehow different than that?
No, it's not. So the chapter says a little bit about this. So when you write an F-star top level definition like this with several asserts in it and all kinds of other proof obligations, like maybe you're calling this lemma and this lemma has a precondition, and that's also it's an assertion in disguise. What F-star does is it generates a single formula that represents all the proof obligations of this top level definition and presents this large formula to the SMT solver to try to prove together. This means that the presence of one assertion. So an assertion is really like a cut in the proof. It says, the way it's represented in F-star's logic is if you assert P, it looks in SMT like proof P. It looks like P, and P implies the continuation. So it inserts a sort of a cut in the proof. So so I think this was a question you had on Slack, Alex. So an assert is more it serves it both plays the role of checking whether a particular fact is true at a certain point, but it also serves as an assist to the continuation so that it can use that fact to prove whatever else follows. And that includes providing patterns for quantifier instantiation and so on as well. I
think I misinterpreted part of what Alex said, so maybe Alex can fill in the detail.
No. I mean, I only asked why queries, while the function itself did not contain anything that, in my imagination, would lead to the query being split. Like you said, multiple queries, while the function we were checking had only one, had no assert spin-offs that would force the query to break into several.
So F-star does not guarantee that there is a single one. So for instance, there will be, if when writing the type of your program, of your top level definition, if the type itself had some proof obligations, the proof obligations associated with the correctness of the type would be a separate query, for instance.
So the precondition, if the precondition is complicated enough that it needs some checking, it will be another query.
It'll be another query. And also, if you what F-star also does is, if in this particular case, when it fed this large query to the SMT solver, the query failed without the SMT solver being able to produce a partial model. So F-star was not able to produce an error report from that partial model. So what F-star does in this case is that, and this is a feature that was added, I don't know, 3-4 months ago, is that when that happens, F-star is then going to split this large query into several small queries, each with an individual assertion in it, and feed that to the SMT solver, feed each of those queries separately to the SMT solver to try to isolate which one actually failed. So this is another situation in which a program the proof obligation of a program can be split into, arbitrarily many queries.
But if the proof is valid, like it's verified, then probably it went in single
Yes.
query for the body.
Yeah.
I mean, skipping the precondition and postcondition part, it was in single query for a valid definition.
That's right. That's right. I mean, there are caveats to this, like if you do use a tactic or if you use spin-off, and there are many other ways in which you can split up.
Yeah, so far I'm not using tactics. I mean, what is the, how do I even phrase it? What is the downside of artificially splitting your big LED definition, big top level definition into several queries, as that, in my vision, should improve performance?
It's actually usually much slower.
Why?
Because you feed a lot. The SNP solver is optimized to do, it's to search in this exponential search space in a very efficient way. And if you feed it a query, it can figure out that this branch of I can sort of finding a proof for one branch of the query can assist the proof of another branch of the query. Whereas if you split the query into n separate queries, you're removing that, you're insisting SNP solver to do fresh searches for each query. So there's no sharing, so it can be slower.
Okay, it's just that I wrote many lemmas split, like artificially split in auxiliary lemmas, top level auxiliary lemmas, just for things to get quicker. Because when I carefully split the proof into smaller parts, each smaller part took like, well, from hundreds of milliseconds to seconds. And
well, that's true too. I mean, in a way, if you wrote your entire program as a single top level definition and fed it to Z3, then like that's not
it crumbles.
Work either,
it crumbles, right? Of course, it crumbles.
So there's kind of a trade-off. Like you got to find the right levels of abstraction in which to work, where you decompose your proof into the right number of lemmas. But for a given lemma, if you can get the proof of that lemma to go through, I mean, an individual lemma may have many assertions in it, but if you can prove all those assertions of the lemma like simultaneously, it is often faster than proving every assertion of that lemma separately. But this is all of this is empirical. It depends on your particular development.
Yep. It's just that I faced the opposite problem.
I should keep moving because I have 15 minutes and I want to cover some more ground.
I had to split it into several auxiliary lemmas because otherwise I would have needed Z3 resource limits in just ridiculous numbers to get it verified. Yeah, and the split versions.
Alex, I should move on because I have 15 minutes left. And
sorry. Yeah. Okay, I'm muted now.
And I'm grateful to Alex for actually providing this example, which is quite in a way similar to. It has some similarities to the example that I showed you earlier from Zeta. And I wanted to give you a sense of, I mentioned that the remedy in Zeta was to use this style of making a quantifier opaque. And I wanted to show you how that works in the context of a much smaller example so that you can appreciate what's going on. So here is an example from Alex where it has a quantified fact in the hypothesis where this is a quantifier alternation of for all m exists n, and it turns out that this leads to this particular alternating pattern leads to a unbounded number of quantifier instantiations, which can cause the solver to kind of go off the rails. And here you see that it actually takes quite a long time, and then eventually
sometimes it verifies.
And it's actually, in this case, it's going to succeed after splitting the query into many smaller queries. So we're not in a very happy place with this particular example right here. So what's the remedy? One style that you can use to address this kind of issue is you can mark your definition as with this attribute saying opaque to SMT. And when you do that, this particular quantifier is not encoded to the SMT solver at all. Instead, what you can do is to write a lemma that's going to control quantifier instantiation. So this lemma, instantiate unbounded, says if I have a function that satisfies this refinement that it's unbounded, and some bound M on which I want to instantiate the assumption, then I can get the body of the, I can get the instantiation, and I get this instantiated fact that there exists an N such that the absolute value of f of n is greater than M. But I control and for the proof of this particular lemma, in order to do this proof, I can selectively reveal the definition of this unbounded predicate in a scope by using this utility from F-star standard library, reveal opaque, which within the scope of this lemma reveals this quantifier to SMT. And in this context, the SMT solver can instantiate it, and I get this proof of this lemma. But now whenever I want to instantiate unbounded, I'm going to call this lemma rather than letting the SMT solver do it for me. And in that style, the proof of this lemma that Alex had earlier, wherever I want to instantiate f, I call this lemma explicitly, and now the proof goes through instantly because the solver no longer has this alternating quantifier in there. And now you have to think a bit more about where you want to instantiate. So it turns out for this particular proof, there's two instantiations, one there at M and another one in there at M1. So you have to think about this, but you get control back, and your proof gets to go faster again. Now, I also wanted to say a little bit about this proof has these two asserts left in it. And these asserts actually, if you remove them, the proof will fail. And the reason these asserts are important here is because what we're trying to prove in these contexts, we now have an existential formula in the goal. This is our goal at this point is in exists I, or actually right there, exists I. And the SMT solver treats existential formulas in the goal exactly like it treats universal formulas in the context. So it's not going to be able to prove your existential formula in the goal until it finds an instantiation for I based on choosing a pattern for a subterm that appears in the existential in the body of the existential formula. And what this assert does is it gives to the SMT solver an active term whose shape is G of N1 minus 1. And that provides the pattern that the SMT solver needs to instantiate this quantifier, and then the proof goes through. But this is quite subtle, and you have to know how to instantiate this assert explicitly. I mean, you have to know that you need to call this assert here. So the chapter covers several styles in which you can instantiate existentials, but maybe the nicest and most explicit style is to instantiate that exists yourself, explicitly by providing a witness. And I just wanted to, in another part of the book, we look at this notation for working with quantified formulas in F-star. And one of them allows you to introduce existential formulas explicitly by providing the witness without relying on the SMT solver. Without relying on the quantifier instantiation heuristics of the SMT solver. So here, rather than doing some assert and hoping that it goes through, you can say explicitly that I'm going to prove this existential by instantiating I with N1 minus 1 here and N minus 1 here. And this is, I think, the cleanest, most explicit way of doing things. I wanted to do one more example, which is also here. So, question was it?
Not quite, but one of ways of avoiding asserts, I wrote it in the chat, but you probably can't read it as you're looking on your screen. If you, instead of asserting that, write instantiate unbounded if with argument N1 minus 1, it also will succeed. And that is probably the least obvious way of fixing the lemma if you remove the assertion.
Yeah, I mean, there's lots of ways to do this. The chapter covers many different variations. You should, yeah, I encourage you to read, and there's probably, yeah, many ways to do this. I just wanted to show you what I think is the cleanest, neatest way, which is to do it explicitly.
Yes, the syntactic
let me
the
go
new
on, Alex.
syntactic sugar.
I have 7 minutes and I want to finish.
Okay.
The chapter also covers how to design a library with SMT patterns. So when you're writing a lemma in F-star, and many of you have probably seen this style in the F-star standard libraries, where you can decorate a lemma with a pattern, and this effectively encodes it to the SMT solver as a quantified assertion with this as the pattern. So here I have a library encoding sets, and have a lemma about how to reason about membership in unions. And what this SMT pattern says is that if I want to prove that X is a member of the union of S1 and S2, I can rewrite this into this disjunction, prove that X is a member of S1 or that X is a member of S2. And so this kind of the choice of these patterns orient equalities in quantified formulas as you can start to think of them as rewrite rules, because this is a left to right rewrite with this particular pattern. Now, what this means is that I can write client programs and reason about sets with respect to this interface and these particular quantifier instantiation rules. So, for instance, here I can ask Z3 to prove that 0 is not in the set 1, 2, 3, 4, 5, and it's going to do this by instantiating this quantifier repeatedly and then showing that the disjunction of X naught for each of the singletons is not true. Okay, but I wanted to also impress upon you that that you should be careful when you do this, because you could choose the wrong patterns here. So for instance, suppose I tried to orient the rewrite rule in the other direction, and I chose my patterns to be the terms that appear on this side, mem of X S1 and mem of X S2. And I put that in my context. Now, if I ask Z3 to even prove this simple fact, it takes forever, and eventually it fails. And that's because what this has done it has introduced a quantifier loop. So so now think of what so this is saying for every pair of mem x1 and mem x2, I can instantiate the quantifier. So effectively, the instantiations I get are something like mem 0, mem 0, 1, and mem 0, 1 allows me to derive mem 0, 1 union 1. And then I can keep going, and then I'm going to get, mem 0 of 1 union 1 union 1. And this goes forever, right? So if you choose your quantifiers, your patterns poorly, you can end up in quantifier loops, and even simple facts can fail. So if you're going to use SMT patterns, do read the chapter, and you can ask and also ask questions about, is this a good choice of patterns for your particular library? And if you choose your patterns well, this can be very productive. If you choose it poorly, you might be digging yourself into a big hole. So that's all I wanted to say. I think we still have 3 minutes or so if there are any more questions.
There's a bunch of questions from the chat.
Okay.
So just walking down. Wojciech asked if basically you talked about opacity being one way to control what is sent to SMT, but if there's other ways to kind of hide things other than opacity.
Ultimately hiding stuff from the SMT solver means some form of opacity, like within, and it's a question of like at what scope you want to hide things. Like, so the pattern that I showed was to make things opaque in the top level context and to reveal them in selected local context. You can, there are many other styles that you can adopt for this. So things like, you can prove a certain fact within the context of you may have a large proof, and you may want to decompose the proof into smaller pieces, and you can well, I don't think I'm going to formulate a coherent answer verbally. Like, there's many styles of opacity, but they all boil down to some kind of opacity at the end of the day.
Our next question from Shira, who asks, basically, if you have a query, an F-star query that succeeds, but it tells you that it did so only with a split proof, like, what do you do about that?
Personally, I would accept it. I mean, it's up to you, like, to decide what style you want. Sometimes I find that if this happens, you can either just take the advice that the error message gives you and turn on split queries. So, for instance, if we go back here, this particular one, if you turn on split queries, it actually goes through pretty quickly. Now, this may be your first response to, like, turn on split queries, and that might solve your immediate problem. On the other hand, you might be masking some other underlying problem, and if you just use split queries a lot, you may eventually come across some other proof in your development where split queries is not the hammer that's going to save you. So it's something you can kick down the road with split queries, but it may be worth trying to figure out why the original query is taking so long. Now, I know in Shira's context, like, Shira, I know you're doing a lot of low star proofs, and there, I think sometimes, like, you don't necessarily have control over everything, because a lot of it depends on what the libraries already provide you. So, if you find that, like, reasoning about modifies clauses is difficult, there's not that much you can do about it, because the libraries are offering you these lemmas with this particular quantifier instantiation strategy. So in that case, maybe split queries, if it works for you in some, I know many people who actually just use split queries, so it's not necessarily a bad thing.
And our final question in the chat, at least for now, is from E, who asks about, like, other pain points of Z3, like nonlinear arithmetic, and bit factor stuff, that kind of stuff.
Yeah, good question. So nonlinear arithmetic, I say a little bit about it in the chapter. I think by default, F-star enables nonlinear arithmetic, but many F-star developments actually disable nonlinear arithmetic in the SMT solver, including, for instance, in that Zeta project, we don't use nonlinear arithmetic. There's a setting you can put you can pass to F-star that will then disable this in the SMT solver. If you do that, then even some simple nonlinear facts, you're going to have to call lemmas from F-star's math library to explicitly prove them. That's going to make things a bit more robust and predictable, at the cost of you having to be more deliberate about your proofs. We're a bit over time, but I don't mind sticking around if there are still questions.
I actually have one question. I've seen a few times in F-star where one would use opaque functions that are, selectively revealed to be earlier definitions, like this unbounded thing. But one thing I've seen a few times is actually opaque versions of equals, like seek.equal.
Yes.
And I just want to know, like, what is the role of, like, opacity for equality? Because is it just for instantiating quantifiers correctly?
Yes, seek.equals is an interesting one. And actually, that I mentioned something about, there's a similar one for set. This set library has an equals as well, right here. And I say a little bit about it in the chapter. The thing is, this equals is a It's an extensional equality on sets, and its definition kind of involves, there are two pieces to it. It involves a quantifier on the one hand, about pointwise equality of membership. And on the flip side, from equals being able to derive sort of provable equality of the sets involves using a representation for sets that's like that has these like domain restricted functions on which you have extensional equality. So all of those details, like we don't want to have to reason about that at every. We just wanted to hide all of that. Like, so you're not reasoning about domain restricted functions with quantifiers at every step of your proof. So it's an abstraction thing, and so we prefer to hide the definition and selectively really invoke. If you just assert equal, that effectively triggers this lemma and lets you move between equal and provable equality.
I guess I'm actually still a little confused because like, what is the definition of like union in this? Union, like my question is more like, you're treating equality as, this quotient type, right?
Mm-hmm.
But it seems like, getting rid of these two equal, intra-equal lim things, you could just interpret everything as just proving F star equality at the end, right? Do you see my question? Sorry, my question is like this. So are you saying this equals thing is used mostly to guarantee extensional reasoning where F star would only guarantee like uninterpreted equality, but it would somehow miss out on the fact that these two sets are somehow extensionally equal?
That's right. Like, so you could, you could prove that, I mean, to reason that, if there was no abstraction here, if there was no interface, and we reasoned directly against this implementation, which is kind of, I think, maybe what is, that's a straw man version of what you're proposing, perhaps, right? And if you did that, then, and you wanted to prove that, say, union of xy equals union of yx, then you would have to reason about these lambda terms at every step and get the SNP solver to reason about extensional equality of this domain restricted lambda term at every step, which it actually will not. You may be able to get it to do it for very small instances, but it will fail at larger instances. So this abstraction boundary is kind of giving you a more, I don't know, a robust abstraction in which to reason about extensional equality.
I see. And there's one more question from Shira again about the difference between a proof passing in Emacs versus a proof passing in a makefile.
That's a frustrating situation to be in. If
Shira can elaborate more on that.
I mean, I can say a little bit about it, which is that so the SMT solver is when you presented a query, Z3 is deterministic. It provides a guarantee of determinism, but its guarantee is very, very narrowed. If you present it with exactly the same syntactic text and the same options, it will respond in the same way. But if you change anything, including you change a variable name, that guarantee of determinism no longer applies. Like the behavior can change because it's using a bunch of many syntactic heuristics for it to help that it uses to break ties when searching this large space. So when you're feeding a query to the SMT solver interactively, but in your Emacs buffer, maybe by presenting it once, retracting it, and presenting it again, this is producing syntactically different theories for the SMT solver. And if you have a proof that is, usually this happens if you're working with a proof that's already kind of on the limit. You're using Z3 R limit 500 or something, at that point, the SMT solver is kind of at its limit, trying to search this large space, and now small perturbations can double the resources that it takes. And your proof, which was working with R limit 500, may now suddenly require R limit 1000, and at that point you're lost. So yeah, it's an unhappy situation to be in. I think if you can avoid being in the situation with, usually I don't use, I mean, we all have our different R limit tastes, but I usually think like a proof that's using more than R limit 20, 30 is kind of asking for trouble.
Okay, well, I think we're probably out of time. So why don't we thank Nik?
Great.
And
Thank you all for the questions.
Yep, thanks a lot.
And sorry
was
to
very-
kind of cut
very
you off
good
at some point, Alex, but I appreciate all the questions and advice and help. See ya.
thank you.
Thanks.